Okay, hello everyone. So let's start today's session. So this is the fourth week of this live session. So today I will first discuss the previous week's assignments, few of the previous week's assignments, and then I will get to the some equivalence problems related to equivalence relations and functions. Okay. So first problem over here we have two sets A and B. The set A is given as 1, 2, and 3. And B set is given as ABCD. So PA is set as the cardinality of the power set of A. So PA is basically the cardinality of the power set of A. And PB is set as the cardinality of the power set of B. So which of the following is true? So first, let's find out what is the cardinality of power set should be. So if this set so if a set is given as a cardinality of a set is given as n, then what is the cardinality of the power set? So power set should be 2 to the n, and we can very easily prove that. So how? So consider any subset A. So now corresponding to each of these elements, so let us consider all of these elements are something like this: A1, A2, A3, A4 up to An, and this brings the set S. So we want to find out what is the cardinality of the set S is n, and we want to find out what is the cardinality of the power set of S. So in order to do that, we just consider any subset A, and we try to figure out how many such subset can we really generate. So for each of this element, A1, A2, A3 up to An, for each of this element, either A1 can be in the set or it cannot. And if A1 belongs to the set, so that would count one set, and if A1 does not belong to the set, so that will count another set. So this way, we can consider all those set that contains A1. Okay. So if we consider the set A, and if we want to count how that all possible number of such subset A of S, then we can just say that okay, so A1 can either contain A1, sorry, A can either contain A1 or it does not. Similarly, A can either contain A2 or it does not. So the total number of A1, sorry, so the total possible number of sets A is basically 2 to the power n. So that, that is 2 times 2 times 2 up to 2 n many. Why? Because A1 can either be in Z, so or it cannot. So that gives us two sets. Then A2 can either be in the set or it cannot. So that also gives us two sets, and we just multiply all those values, and that gives us 2 to the n. So anyway, so if cardinality of a set is n for a finite set, obviously, then we can say the power set of S, the power set of A is basically 2 to the n. So over here, since the cardinality of A and cardinality of B is given as 3 and 4 respectively, so corresponding to that, we can say that the cardinality of the power set should actually be 8 and 16. Okay, so 8 and 16, that should be the cardinality of P and P. Sorry, the value of P and P. So now, if we try to check all these equations over here. So PA plus PB is equals to 7. This definitely is not true. PA times PB is 32. This is also not true. Now PB is 2 times of PA. That is true. Because as you can see that PB is 16, which is 2 times 8. And finally PPA times PP is equals to 120. So now what is PA times PP? So it is 2Q and this is 4. So that should be 2 to the power 7. And 2 to the power 7 is nothing but 120. So yes, this is also true. So C and D, these are the only true, are only true, and these two are not. Okay, so now let's get to problem number 2. So in problem number 2, we are given a set A, which is 1, 2, 3, and we are also given a relation. Now we have to find out whether this relation is symmetric, antisymmetric, or what. Um, okay, so first, so the best way to do this is basically we just first generate the matrix. So the matrix would actually be a 3 by 3 matrix. Now over here, 1 1 is there. Okay, so 1 2 3. So corresponding to 1 2 and 3. This is corresponding to 1 2 3. So 1 1 is there, 2 1 is there, 1 2 is there, 1 3 is also there, 3 1, 3 2, and 2 3. Rest are 0. So this is the matrix corresponding to the relation. Now, is it symmetric? So definitely it is a symmetric matrix. As you can see that for each pair AB that belongs to the relation R, we can also see that BA also belongs to the relation R. Because so for 1 2 2 1 belongs to R, for 1 3 3 1 belongs to R, and for 2 3 3 2 belongs to R. And similarly for 1 1 1 1 definitely belongs to R. So for these cases, we can see the corresponding the corresponding I mean for AB pair, BA, the corresponding BA pair also belongs to the relation. So this is definitely a symmetric relation. Now, what was the condition for antisymmetric relation? So for antisymmetric relation, the condition was that if this is true, that AB belongs to R and BA belongs to R. If in any case this is true for a relation R, then that should imply that B is actually equal to A. And this is true for all A and for all B. So this was the condition for antisymmetric relation. Now the question is whether this is a antisymmetric relation or not. So as you can see that over here 1 2 belongs to R and 2 1 belongs to R, but 1 is definitely not equal to 2. So this is not an antisymmetric relation. So the first option is not true, which says that both antisymmetric and symmetric. Second case, which is that it is not symmetric but antisymmetric, this is also not true. As you can see, this is symmetric relation, obviously. And the third condition says that it is neither symmetric nor antisymmetric. That is also not true. So option D is the correct option. That is, this is a symmetric relation but not an antisymmetric relation. Okay. So let's get to problem 3. So in problem 3, what we have here is following options, and we have to select the correct option. So first, we are given a relation, and it says that it is a relation on a set on a given set 1 2 3 4 5, and the transitive closure is given as this. So we have to see whether this is true or not. Now, what was the algorithm to find the transitive closure? That was the Horschel's algorithm. So we will use Horschel's algorithm for this particular case. So here we have the set S as 1 2 3 4 5. Sorry. So first we just write down the matrix. So the matrix is given as this: 1 3 is there. So 1 3 should be 1. 3 4 should be 1. So 3 4. This is 1. 1 1 is 1. 5 5 is 1. And 4 5 is 1. And rest of them should be 0. So this is the given matrix. So this is considered as our W0. Now, what we have to do is that at each step, we just have to update this matrix. And how the update works? The update rule uh, for key for the kth iteration, we say that this is actually equals to ijk minus 1, or sorry, this is equals to 1 if any one of this condition holds, that this is equals to 1, or the wik in the key minus 1 in the key minus 1 matrix is equals to 1, and the kj element in k minus 1 matrix, both of them are 1. Okay, so this was the update rule for this matrix. So now we have been given this W0. So now we have to find out what is W1. Okay. So first of all, let's copy this. So now we have to find out what is W1. So in order to do that, so first we have to, so basically whatever is Wij minus 1, we can just wherever the value 1 was, we can just assume that over there the value 1 would be. Now 1 would be there. So now we have to see if any other positions, we can update those positions or not. So in order to do that, so over here, as you can see, that we are taking the ith column over here. So the so I can run over from 1 to n. Okay, so we are considering an n by n matrix, and j can also run from 1 to n. Now, if I is running over from 1 to n and k is fixed, so this is nothing but the kth column of W. Sorry, yes, kth column of the matrix Wk minus 1, and this corresponds to the kth row of the matrix Wk minus 1. So we just first, so for W1, we just first take the first column and first row. So we just write it over here, 1 0 1 0 0, and then 1 0 0. So first column over here and first row is over here. So now we have to see that if we can update this. So update rule was that if if Wik is equals to 1 and Wkj is equals to 1, then we update Wij as 1. So what is Wik? So okay, so corresponding to this, okay, so as you can see, 1 and 1, so this should be 1. Over here we can see that 1 and 0, so this should be 0. 1 1, this is already 1. And for the first row, basically there should not be any update, because this is 1 0 1 0 1, so no update is there. And since all of these are 0, so any update, this rest of the rows should not be updated. So this is W1 itself. So in W1 there is no update. Okay. So now let's go to W2. So this is our W. So for W2, we just need to take the second row and second column. Now we can just skip this part, because the second row, as you can see, this should be all zeros. Second row is basically all zeros, and second column is also all zeros. So since none of the columns or none of the rows are basically have one value, so no update would be there, because the update route was that that both of them should be 1, then we can update that particular cell. And since none of these are 1, so we can just expect that no update would be there. Okay. So now let's go to W3. So in W3, we just take the third row and third column. So the third row, sorry, third column over here is 1 0 0 0 0, and the third row is 0 0 0 1 0. Now as you can see that this one and this one, so they meet up, and now we can update this as our one. So this is the first update. We update it as one. Now, is there any other update? So no, because all the rest of the rows are zero, so there will be no update over here. So this is our W3. So now we have to use this matrix in order to update the. Okay. So this is also our W3. Now we are using W3 in order to update W4. Now for W4, we just have to take the fourth row and fourth column. So the fourth row is basically 0, 0, 0, 0, 1, and the fourth column, which is this one, is 1, 0, 1, 0, 0. So now we have to see which cells can be updated now. So for updating those cells, we just have to need to have both of the elements as 1. So over here we have 1, over here we have 1. So that should update this cell. So this cell should be updated to 1. And over here also, this cell should also be updated to 1. So now we have 3 cells, these 3 cells to be updated. Okay. And no, there should not be any other cells that needs to be updated. Okay. And since there are 5 elements, so we have to go to sort from W1 to W5. Okay. So therefore, we need one more step. So we copy W4 and we need W5. We need to update W5. So now for W5, we need the 5th row and 5th column. Okay. Sorry. The 5th column should be 1 0 1 1 1. Now we do want to update it. So only the last column can be updated, because as you can see that only corresponding to this last column we have 1. And for the rest of the other columns, we have 0. So none of this should be updated. Only this part should be updated if there is an error. And since, as you can see, that corresponding to each of these cases where both of these are 1, each of the cells are already 1. So there is no update. So this is our relational matrix corresponding to the R star. R star is basically the closure of R. So now, what are the values that are here? Okay. So first, sorry. If this is our relational matrix, so corresponding to that, what should be the relation? So we have the relation R star as 1 1 is there, 1 3 is there, 1 4, 1 5. These are there. Then 3 4, 3 5, 4 5, and 5 5. So this should be our R star. Now, in the question, what was given as this 1 3 1 3 3 4 1 4 1 1 5 5 4 5 3 5 1 5. So if we can if we check these two values as these two relations, so they are basically the same. So this is the transitive closure of this relation R. This is our R star, and this should be the R. Now, Remember that this question is different from the one that was given in the assignment. So in assignment, there was some values which were missing, and that's why the problem that was given in the assignment. So for that case, the relation was not R star. That means it wasn't the transitive closure. But I have changed this question a little bit. So this is the transitive closure of this R star. Sorry, this R star is basically the transitive closure of this relation R. Okay, so now the second one is that given this binary matrix, binary relational matrix, so we are given a relational matrix and we have to find out the transitive closure, and we have to verify whether this is the transitive closure or not. So we can again use the Warshaw's algorithm. So the matrix that is given is 1 0 0 0 0 1 0 1 0. So 1 0 0 0 0 1 0 1 0. So this is the matrix that is given, and we have to find out the transitive closure. So this is our W0. Now W1, in order to compute the W1, we can just copy the first matrix, the W0 matrix, and now we have to take account of the first row and first column. Now, is there any update that you can see? So no, because 1 1 corresponding to this 1 1, the cell 1 is already 1, so there should not be any update. So this is our W1 already. Okay, so for W2, we have 1 0 0 0 0 1 and 0 1 0, and we have to take in the account of this second row and second column. So as you can see, corresponding to this, we can update this cell over here. So this cell is updated, and we have 1 over here. So this is our W2. Now, there should not be any other update over here. So now again, what we do is that we copy this matrix for computing W3. So 1 0 0 0 0 1 0 1 1. Now over here we have to take into account the third row and third column. Now corresponding to that, if we try to update this matrix, then we will see that this particular cell, the 2 2 cell, this should also become 1. So this is our W3, or rather, this is the matrix corresponding to the closure of the relation. So in the question, it is given that this is the transitive closure of the relation, but it should actually be, there should actually be a 1 over here. So then we can call it a transitive closure. So this is not a transitive closure. Okay. The time complexity for transitive closure operation is ordered into the 3 over 2, but this is not true, because as you can see, how many operations, I mean, in order to compute the compute this transitive closure, we need n many steps. Okay, so W1, W2, W3, so at each step, so there are total n many steps. So n steps, and at each of the steps, what we're doing is that for each ij, so the update, as you can see, the update rule for each ij, this ij pair, we are just checking this condition, that whether wij k minus 1 is equals to 1 or not, or wik k minus 1 is equals to 1 and wkj is equals to 1. Okay, so this is what we are checking for each of this pair ij. And how many ij pair are there? Because I is running from 1 to n and j is also running from 1 to n, so there are total n square many such situations. So therefore, there are n many steps, and at each steps there are n square many steps. Sorry, so there should be n many iterations. Instead of saying steps, you can say that there are n many iterations. And at each iteration, we have n square many steps. That is, this n square many checks that we have to compute in order to find out the Wij. So therefore, the total number of steps is basically n cube steps. That is, it is order n cube. The algorithm runs in order n cube rather than order n cube over 3. Sorry, n over 3 over 2. So this is not true. And none of the given options are correct, so this is also definitely not true. Okay, so now let's go get to the problem with some set theory problem. Okay, so here we have to choose the correct statement. We are given 3 arbitrary sets A, B, and C. So now, when we say that these are 3 arbitrary sets, it doesn't mean that for all arbitrary sets this is true. Okay, so what it says is that there exists some set which does not have any some special property or anything. So we are just given 3 arbitrary sets, and when we are arbitrarily choosing this set, we are fixing those sets. Okay, so it's not like these conditions are true for all. Okay. So there are some arbitrary sets, and we have fixed those sets, and for those fixed sets, these conditions are true. Okay, so then it wants us to check whether this is true or not. So the first condition is that A union C is equals to B union C, and that should imply that A is equals to B. Okay. So basically, what we have to do is that we have to find out either we have to prove or disprove. So in order to prove, we just have to use the rules of proving mechanisms in order to prove this. Or if we say that this is not true, then we just basically have to give an example for which this is not true. So that means we just have to give an example of 3 sets A, B, and C for which this is not true. Okay, so it says that A union C is equals to B. Sorry. Okay, so first it says that A union C is equals to B union C. Right, and then it should imply that A is equal to B. So we are going to show that this is not true, that is, it is false. So basically, we're just going to give some example. So let us consider that A is our set 1, 2, 3, and C is our set 4, the singleton set 4. And consider B as our set 1, 2, 3, 4. So for this case, we can say that A union C, that is actually equal to 1, 2, 3, 4. This set. Again, B union C is this set 1, 2, 3, and 4. That is, for this example, we can say that A union C is actually equal to B union C. But that does not imply that A is equal to B, because as you can see that A does not have this element 4 and B do have this element 4. So A is not equal to B. So we have an example where this is true, but this is not. So this is false. Okay. So the second example says that about intersection. So we have to either prove or disprove it, that A intersection C is equal to B intersection C. This implies A is equal to. Now again, this is false. Now we can prove this by example. We just choose A, B, and C in this way. 1, 2, 3, 4. B as 2, 3, and 4. And we take C as 2, 3. Then A intersection C is basically 2, 3. B intersection C is also 2, 3. That means that A intersection C is equals to B intersection C. This is true, but that does not imply that A is equal to B, because as we can see that A is not equal to B. So this is also false. So in the third example, we are given that A union C is a subset of B union C. And A intersection C is a subset of B intersection C. Then we have to prove that, so both of them implies that A is a subset of B. So this is what we have to prove. Now, what we can say is that A can be written as A union A intersection C. Now, this can now be written as A union B intersection C. Sorry, this is a subset of this. Why? Because A intersection C is a subset of B intersection C that is given to us for any arbitrary C. So this can now be considered as A union B intersection A intersection C. Sorry, A union C. Why? Because of the associative property of union and intersection. So from there we can write this. So now this can now be written as intersection B union C, because this is a subset of this, because A union C is a subset of B union C. Oh, by the way, in order to do this, we must also have this properties known. That is, if A union B is a subset of A union C, if B is a subset of C. Okay, so if B is a subset of C, then we can write this, and similarly, if B is a subset of C, then we can also write this. So this can be easily shown. You can check that. So using that, we are writing this, that since A intersection B is a subset of B intersection C, so therefore we could write this, that this is a subset of this. Again, this is a subset of this because A union C is a subset of B union C. That is given. Okay. So from here, we can again use the associative property to write it as A intersection C union B. Now A intersection C, that is a subset of B intersection C. So we can write it as B intersection C union B. Now B is the set B union with an intersection with some arbitrary set C. So that should actually give us the set B. So now we have just proved that A, we have started with A, the set A, and we have proven that the set A is nothing but a subset of. So this is a direct proof method, and we have proved that this is true. Now the problem is that the other way does not. In order to the other way hold, we must have B union C is a subset of A union C, and similarly, B intersection C has to be a subset of A intersection C. So then we could say that, okay, B is a subset of A, and then we could say that A is equal to B. But since this is not given to us, so we cannot really say this, and therefore this A is equal to B is actually not true. So C is true, but D is not. So is not A. Okay. So now let's start with some problem with relations. So we have given a relation over here, which is the relation R, and the relation R is defined as this. So let's say the relation R is defined over the set of all students. So let's say alpha beta are two students and alpha or beta are related, if and only if student alpha and student beta have at least one class in common. and alpha is not equal to beta. So then we have to choose the correct answer. So first we said that if alpha beta belongs to R square, so what is R square? So R square is basically the composition of R and R. So let's say that there are two relations. R is a relation that is a relation from A to B, and so this is not really a function, but rather, okay, so this is actually functions. So let's say that R is a relation from A to B. That is, we say that an element A in the set A is related to an element B in the set B if AB belongs to R. This pair belongs to the relation R. Okay, so we consider that from A to B there is a relation R, and from B to C there is a relation S. So R compose S is actually the set of all AC in A cross C such that there exists a B in B such that this AB such that this AB belongs to R and BC belongs to S. Okay. So this is how the R composition S is defined. That is, in order to have a relational mapping from A to C, we must have intermediate value, intermediate element B in this set B, such that some A is related to B and that particular B is related to C. Okay. Then we say that this AC pair is actually in the relation R cross S. Sorry, R composition S. So this is how the composition of relations works. Okay. And similarly, so R square is basically R compose R is it is nothing but so over here for this case, since we are considering the set of all students, so it says that this is the so let us consider that S is the set of all students. Okay. This S is the set of all students. Then this is S cross S. Alpha beta is belongs to S cross S such that there exists a gamma in the set of all students such that alpha gamma this belongs to the relation R and gamma beta this belongs to the relation R. So this is what the definition of R square is. That means there should exist a gamma such that alpha gamma shares a class. I mean the relation R is defined as this if alpha and beta they both share a class with each other and alpha is not equal to beta. So alpha gamma should share a class and gamma beta they should also share a class. Okay, so then we consider that relation to be R square. So first option says that if alpha beta belongs to R square, then alpha beta are at least two classes in common. So this is not true. So we can give an example for that. Okay. So let us consider that the set of all students is basically 1, 2, and 3. And let's say that 1, 2, the relation R is given as 1, 2, and 2, 3. So that means that 1, 2 have a class in common, and 2, 3 have a different class. Let's say, okay, so let's say there are two classes. Class 1 is basically English and mathematics. So in English class 1 and 2, they share this class, and 2 and 3 shares the mathematics class. So 1 and 2, they both have one class in common, and for 2 and 3, they also have one class in common. Now, what R square is? So R square is basically 1, 2, 2, 3, and 1, 2, 2, 3, and 1, 3. Okay, so now even though r square is, so if we consider 1 3 in r square, so as you can see 1 and 3, they don't have any classes in common at all. Okay, so when we say that alpha beta is in R square, then alpha beta has at least two classes in common. So that is not true. It may happen that alpha beta do not have any classes in common at all. Okay, so this is not true. Okay, the second option says that if there is, so if alpha beta belongs to R square, then there exists a gamma. Says that alpha beta and gamma all have at least one class in common. So as you can see that this is also not true, because uh, for 1 and 3 they have no classes in common, and still 1 3 belongs to this R square. In fact, it does not exist such gamma for this particular example, for which we can say that alpha, beta, and gamma, they all have the same class. That is, 1 2 3 does not have one class in common. So this is also not true. If alpha beta belongs to R star, so R star is basically the transitive closure. So R star is basically a transitive closure. So it says that if alpha beta belongs to the R star, then alpha and beta should have all classes in common. Okay, so we will get to that. So finally, we have alpha beta is in R square, then there exists a gamma, says that alpha and gamma are in at least one of the common classes, and beta gamma in at least one of the common classes. So that is what we have seen over here. That is, there must exist a gamma such that alpha and gamma is related and gamma beta are related. So alpha gamma are related, that means that alpha and gamma they share a common class, and beta gamma they also share a common class. But it might not be necessarily true that this alpha gamma with this class shared by alpha and gamma is same as our class shared by gamma and beta. Okay, so this is true. So now this option C. So if we say that alpha and gamma is actually in R star, that is a transitive closure, then what can we say about alpha and gamma? Sorry. So let's say alpha beta, this belongs to R star. And let's say, let's consider that they have, or rather, so than they have, let us consider that there exists one class C, such that alpha belongs to that class, but beta does not belong to that class. Now the question is, can this happen? Now, if this is possible, that alpha is the only one in the class, alpha is the only one in the class C, but beta is basically like this. So alpha and beta shares every other class. So let's say there are three classes or four classes. Let's say C1, C2, C3, and C4, and all of the classes are shared by alpha and beta, both of them. But C1 is the only class where alpha is alone. And let's say gamma is another student where gamma is basically uh, is in class C2, C3, C4, and everyone. And delta is also another student where delta is in class C2, C3, C4. But C1 is the only class where alpha is there, but no other student is there. Only one student in the class. Then can we say that this is a transitive relation? Because alpha is not related to alpha itself. Because the relation is defined as this, that if alpha and beta are students, that they have at least one common class, then we say that alpha and beta are related. Uh, if and also there should be this condition that alpha is not equal to beta. So this is also important. So over here, as you can see, that alpha has the class, say alpha attains this class C1. Alpha is the only one who is attaining this class C1. So in this case, uh, alpha is not related to alpha, but alpha is related to beta, alpha related to gamma, alpha related to delta, and similarly beta is related to alpha, gamma, delta. So this relation, if you check, then you will see that this is also a transitive relation, because everybody is related to other one, because they have at least one class in common. So we can say that they are, so alpha is related to everyone else, and beta is also related to everyone else, and so on. But the condition that it says that alpha beta they have all classes in common, so this is not true, because alpha have class C1 but beta does not have class C1. So even we can consider C5, C6, C7 such that beta, gamma, delta, they all have their own separate class. No one else attend those classes. So even in those cases, even we can include gamma, and over here we can include delta or whatever. Even then, this relation states to be transitive, because these four students, alpha, beta, delta, gamma, they have at least one class in common, where all of them attend this class. So if that is true, as long as that is true, that all of the students are in the same class, at least one class is there where all of the students attends this class, then we cannot. So then this relation is always a transitive relation. So if alpha beta is in R star, then alpha beta have all classes in common. This might not be true. So this is also not true. Okay. Now let's get to problem 6. So problem 6, it says that R1, R2, R2 equivalence relations, and the relations are on a non-empty set, and which of the following is true? So first one is given as R1 union R2, and the second one is given as R1 intersection R2. So first one is not a equivalence relation, second one is. So we will give an example for first one, such that we will see that R1 R2 has two equivalence relations, but their union is not. And then we will give the proof for the second one. Okay, so let us consider a relation on a set 1, 2, 3. We consider a set 1, 2, 3, and on that set we define this relation 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. And similarly, our R2 is basically 1, 1, 2, 2, 3, 3, 2, 3, 3, 2. Now, both of these relations are equivalence relations. Why? Because this is reflexive, because 1, 1, 2, 2, 3, 3, this these belongs to this R1, so this is definitely reflexive. What about symmetric? So for symmetricity, if A and B are not equal, and we see that this AB pair is in the relation R, then BA pair should also be in the relation R. So as you can see, 1, 2 is in the relation R, so that implies that 2, 1 should also be in the relation R. And 1, 2 and 2, 1, they both belong to R1, so definitely this is symmetric also. So, and for R2, 2, 3 and 3, 2, they both belong to this relation, so therefore R2 is also symmetric. So both of them are reflexive, symmetric, and finally we have to prove that these are transitive also. Now for transitivity, as you can see that 1, 2 belongs to this relation, 2, 1 also belongs to this relation, then 1, 1 should also be in the relation. And that is true, because 1, 1, this is the relation is already reflexive. And similarly, 2, 3 is in the relation, 3, 2 is in the relation, so 2, 2 also be in the relation. So that is also true for R2. So both of them are reflexive, symmetric, and transitive. Okay, so these two are equivalence relations. Now, what is the union of R1 and R2? So you consider that relation to be R. Then the union is basically, so 1, 1, 2, 2, and 3, 3, these pairs will be there already. And then 1, 2, 2, 1, 3, 3. This is the union of R1 and R2. Now, uh, like before, since we have already seen that if we take the union of two relations, then if these two relations are reflexive, then the union should also be reflexive. If these two relations are symmetric, then the union should also be symmetric. But what about transitivity? So this relation R is already reflexive and symmetric. We can, uh, I mean, we can see that. But what about transitivity? So basically we will prove that this is not transitive. So in order to do that, we just have to give an example. So here the example is 1, 2. Sorry, 1, 2, 2, 3. So 1, 2 is there, 2, 3 is there. So that should imply that 2, 3, sorry, 1, 3, 1, 3 should also be in the relation. But that is not true because 1, 3 is not in the relation. So that is, this is not transitive. And since this is not transitive, so this is not equivalence relation. Not equivalence relation. So we have given an example that R1 union R2 cannot be an equivalence relation. It is not always. Okay. So now we have to prove that R1 intersection R2 is equivalence relation for R1 R2 equivalence relation. So first we have to prove. So we have to prove three properties. First is reflexive. Second is symmetric. And third is transitive. First, we will go for the reflexive property. So, in order to prove the reflexive property, what we have to show is that for each A in the set S, AA belongs to the relation R. So, basically, here R is intersection of R1 and R2. Now, we know that for all A in S, we know that this AA belongs to R1 and this AA belongs to R2. So this part we know. And since this is known, so this actually implies that AA actually belongs to R1 intersection R2. Because this was the definition of intersection. If A belongs to R1 and A belongs to R2, then they should also be in the intersection of these two sets. So for all S, this is true. And therefore, we can say that this relation is reflexive relation. Okay. So now for symmetric. For symmetric relation, what we have to prove is that for any AB belongs to R, this should imply that BA also belongs to R. So we consider any element A and B, sorry, any pair AB in R. So this implies that this AB belongs to R1 and AB belongs to R2. Now, if AB belongs to R1, that should imply that BA belongs to R1, since R1 is a equivalence relation, and also BA should also belong to R1. Sorry, BA should also belong to R2. So this basically implies that BA belongs to R1 intersection R. So we started with AB in R, and we have ended with BA in R. So this is also a symmetric relation. And finally, we need the transitivity. for transitivity, we have AB in R and BC in R. Okay, so we have AB in R and BC in R. So since AB is in R, so we can say that AB belongs to R1 intersection R2. So that means that AB belongs to R1 and AB belongs to R2. Now, okay, so AB belongs to R2 and AB belongs to R2. And similarly, over here we can say that BC belongs to R1 and BC belongs to R2 from this condition. Now, AB belongs to R1 and BC belongs to R1. So that should imply that AC belongs to R1 and AB belongs to R2 and BC belongs to R2. That should give us AC, sorry, AB, and over here it should be AB, and over here it should be BC. AB belongs to R1 and BC belongs to R1. That should give us, sorry, that should give us AC belongs to R1 and AB belongs to R2 and BC belongs to R2. That should give us AC belongs to R2. Okay, so this gives us AC belongs to R1 intersection R2. So we started with this and we have ended with this, which is R. That is, AB belongs to R, BC belongs to R. This implies that AC belongs to R. And therefore, this relation is transitive. And since all three properties are satisfied, we can say that this is nothing but a equivalence relation. Okay. So now let's come to the problem 7. In problem 7, we have A, B, and C, these three sets, and there is a relation R is defined from A to B and S to, and from and S is defined from S B to C. We are given this relation on matrix R and S, so we have to find out what is R composites. So there are two ways that we can do this. So first we can do this graphically, and we can also find out the matrix, and then we can apply binary multiplication of those matrices. Okay, so first let us consider the graphical method. So in the graphical method, basically what we have here, we have three sets. So let's draw those three sets first. So we have A matrix with, sorry, the set A with elements A1 and A2, element B with B1, B2, and C with C1, and from B to C, we are defining the relation S. So as you can see, the R is defined as A1 and B1. These are related, so we basically get an H from there. Okay, so we do not need a direction. We just okay. So A1 B1 should be related. A1 B2 should be related. And over here we have B1 is related to C1. B2 is related to C1. 1 is related to C3, and B2 is related to C2. So this is how the relation R and S, we can represent this relations R and S. So now our composition is just that. So A1 should be related to, so A1 is already related to using the relation R. So therefore, in our composition is, we should have A1 C1, A1 C2, sorry, A1 C3, A1 C3, then A1 C1. Okay, A1 C1 is already there. So A1 C2. Yes. So A1 C1, A1 C2, and A1 C3. So this should be in the rotation R composition is. Why? Because the R composition, the definition of composition was that AC belongs to R in this composition relation. If we can find a B in the intermediate set, this B, such that A1 B, A1 B1, this belongs to R, and B1 and B1 C, that belongs to S. So A1 C1 is in R composition S because corresponding to A1 and C1, we can find this B1 such that A1 B1 is in R and B1 C1, this is in S. Similarly, for A1 C2, we have the value B2. So A1 B2, this belongs to R, but and B2 C2, this also belongs to S. And similarly, B1 is the intermediate element for C3 also because A1 B1 this is in R and B1 C3 this is in S. So therefore, these three are the only possible values for A, B, and C. So now A2 is not related to any of these elements because A2 is not related to any of the element in B also. So we cannot. So that it is not possible that A2 is related to any of the element in C. Okay. So, okay. Okay. So we have R composition is like this. Now, this was one way to find this R composition is, and now since we our ultimate goal was to find the matrix related to this, so we can just now draw the matrix and find the matrix corresponding to this one. So basically, we have a 2 cross 3 matrix, so corresponding to A1 A2 and C1 C2 C3 A1. So A1 C1 is there, so A1 C1 is there, A1 C2 is there, and A2 C3 is there, and rest of them are 0. So this is the matrix corresponding to R compositions. Now, what if we can just find the matrix for R and S, and then we find the matrix for R composition is using some matrix operation on those matrices. So that can also be done. So for this, we just find the matrix corresponding to R. So that should actually be for matrix corresponding to R, there should be this, and the matrix corresponding to S, there should be this matrix. So for R, as you can see, A1 B1 and A1 B2, these are the only values over there. And over here, this should be B1 C1, B1 C3, B2 C1, and B2 C2. This. Um, So now we just have to multiply these two matrices. Now the multiplication operation is a little different. It is not the regular multiplication method. So what we do over here is that these are logical operations. And by logical operations, what we mean is that, so first of all, we have, so instead of considering this as 1 and zeros, we can just consider this as true and false. So these are true values and these are false. So true, should also be true. And these are false values. So now, instead of doing multiplication that we used to do in regular multiplication method, matrix multiplication method, we consider logical AND operation or the conjugation. And instead of doing addition operation, we're just going to use the disjunction function. Okay, so basically this should be the conjugation of true and true, and then conjugation of true and true, and then the disjunction of. So this is true, conjugate true, disjunction of true, conjugate true. So this should be the first cell of this new matrix, resultant matrix. So over here it should be true, false, then conjugate with true, true. Sorry, this is a disjunction of true and true. Okay, and finally over here this should be true, true, disjunction of true and false. Okay. And similarly over here it should be false, true, false, true, false, 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 true, false, true, false, false. Okay. So this should be the final resultant matrix. And corresponding to that, what we will actually basically have here is true, 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 false, 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 or rather 1, 1, 1, 0, 0, 0. So this is the relational value that we have. Sorry, the relational matrix corresponding to this R composition is. So in order to find R composition is, what we can do is that we can find the relational matrix corresponding to R and S, and then we can just straight up multiply them together. And the multiplication is a little different. So it is not normal multiplication, but rather it's a logical operations instead of the standard addition and multiplication. Okay. So that is how we can find the R composition is. Or what we can do is that we can just graphically represent the relation, and then corresponding to that, we can find out the R compositions. But graphical method is, since the example was small, the size of A, size of B, size of C was only 2 or 3. So therefore, the graphical method is very easy for this. But let's say we are given given A, B, the size of A, B, and C, all of them are like 5 or 6. So then our graphical method would actually be very useful. So rather, we should just be doing this matrix multiplication operation. We just find out all the matrix representation of R and S, and then we do the composition. Okay. So in problem A, we are given N to be the number of all different equivalence classes on a set N. Now, one thing that we have to remember, we have to recall that when we consider an equivalence classes, so if we consider a set S, and if we consider equivalence classes on that set S, the number of equivalence classes, equivalence relation. So the number of different equivalence relation would actually create different partitions of the set. So partition means that it will divide the whole set into different disjoint non-empty sets. So that means the intersection of any two sets would actually be always phi, that is empty. And but if we union them all together, so that would give us the whole set back. So if we consider this partition as this Px, so P1, P2, P3, up to P1. It is considered that this is a partition of the set. So this is a partition. Then the union of all these Pi's, I is equals to 1 to n. this should also always give us back the set S. And if we consider any two I and j such that I is not equal to j, then pi intersection pj should also always be equal to phi. So this is the definition of partition. And if we consider a partition on a set S, then corresponding to the partition, we will always find the equivalence relation. And similarly, if we find an equivalence relation, then corresponding to that, we will always find a partition. So basically, finding the number of partition is exactly equal to the finding the number of equivalence relation of this. So this is what we have to do. We are given that Pn is basically the set, is the number of all possible equivalence relations on a set of n elements. So this is what is given to us. Now, what we have to show is that okay, so this is the number of so Pn is given as this. So as we have already known to it that number of equivalence relation is basically equal to the number of partitions of this. So basically what we have to do is that the number of we have to find number of all partitions. So partitions on the set of n elements. So this is what we have to find. So instead of finding the number of all possible equivalence relations, what we will find is the number of all possible partitions on the set. Now, this can actually be proven that this relation is true. Sum over j is equals to 0 to n minus 1. N minus 1 comma j a minus j minus 1. Now we can prove this using induction. Okay, so in order to use induction, what we say is that we have to have an initial condition, that is P0 is equals to 1. And since P0 is equals to 1, and 1 should actually be equals to sum of j is equals to 0 to 0. So basically this should be 0 only, and here it should be okay, C0 0. So that should actually be 0 is actually 1. 1 times P0, which is equals to 1. So this should be equals to 1. So P1, what P1 is that P1 is basically the number of ways you can partition a set of a singleton set. So number of ways you can partition a singleton set. So it can only be done in one way. That is, you just have a singleton set. So that is the only way you can do that. So that's why P of 1 should actually be equals to 1. And P of 0 is equals to 1 because how many ways you can partition the empty set. So the only way to do that is to do nothing and just have the empty set itself. So that is the only way. Or rather, we can just say that there is the only way we can do that we do not generate any partition. So this is basically vacuous to prove that P of 0 is equals to 1. And P of 1, oh, okay, so this is giving us our initial condition. And for P of 1, we have shown that this is also equals to 1. So therefore, we can say that the initial condition is true for this. And we consider that for any n less than, not n, for any k Okay, so for any n less than k, this is true. Less than equal to k, the p of k is true, or rather we can just say that p of n is actually equals to this p of n satisfies the relation. Satisfies the relation. Okay. And now we have to prove that for n is equals to k plus 1, this is also true. So for n is equals to k plus 1, we have basically k plus 1 many elements, a1, a2 up to a k plus 1. Now what we can do is that we just select a k plus 1 element over here, and rest of the elements are basically a1, a2 up to ak. So there are k many elements over here, and k plus 1 is one element. So now how many ways can we actually partition this set of k plus 1 many elements? So this is what we have to find out. So one way to do is that so we just have one element over here, and the rest of the element we have over here. We consider the set to be S. Okay, so in the set S, we just consider all the rest of the elements A1, A2, AK plus AK, and AK plus 1 is over here. So that is one way that we can first partition this to element, and then how many ways that how many partitions of this form that AK plus 1 is only a singleton set, and the rest of the element and from the rest of the element we just consider all possible partitions. So that is basically gives us P and PK many partitions, because there are K many elements over here. Now what we consider is that AK plus 1 and one other element from this set. Now, and the rest of the elements should be basically you exclude those two elements, and the rest of the elements should be over here. And over here there should be k minus 1 elements. So how many ways we can do it? So this one element can be chosen from this k set in k many ways. Okay, and then we have pk minus 1. That is, this k minus 1 many elements can be partitions into this many ways. And this is true because we have assumed that this Pn is actually equals to this for any key. For any n less than equals to k. So Pn satisfies so pk. So satisfies the relation. So instead of saying that, so we can just say that Pn represents the number. N represents the number of partitions. Okay. So now again we have k plus 1 many elements, and another two elements are chosen from this set. And so in the S set, we will just be having k minus 2 many elements. So how many ways we can choose this two element? We can choose this in C k 2 many ways. And how many ways we can partition this element? Partition this set. So pk minus 2, and so on. So we will just keep on doing this until and unless this set S becomes a singleton set. Okay, so therefore, we, if we write down all possible values like this, so this will actually give us, and we sum them together, so that should actually give us this C A comma J P K minus J. Yeah. K minus J, and where J runs from 0 to 0 to A minus 1. So 0 to k. So this is what pk should be. Oh, sorry, it is pk plus 1. Pk plus 1. So so over here, as we have seen that all this Pn represents the number of partition, and also Pn follows this relation for all n less than equals to k. Now for k is equals to for n is equals to k plus 1, as you can see that pk plus 1 is actually satisfies this relation. So which is basically same as this one if we replace n by k plus 1. So therefore Pn is true uh, for all n. So that means that this recurrence relation, this Pn, this is actually true for all n. Okay, so now in problem 9, we are given this relation R on the set of all integers. So Z is basically the set of all integers. And it is given that A is related to B and only if A minus B is divisible by n. So n divides A minus B. So now we have to find out whether it is reflexive, symmetric, and transitive. Okay. So now for reflexive relation, can we say that A belongs to R for all A belongs to Z? So A minus A is always equals to 0. Now any number n divides C. Now this is true for any A. So therefore we can say that A definitely belongs to this relation R. So this relation is reflexive. What about symmetric? So let's say that AB is in the relation R. So that implies that A minus B, it is divisible by n. Now if A minus B is divisible by n, so what can we say about that? That n is actually, A minus B is actually equal to some n t, where t is some integer. So that should also imply that b minus a is actually equals to n dash, where t dash is actually equals to minus t. Then we can say that. So this also implies that n divides b minus t. That implies that BA also belongs to this relation R. So if it belongs to R, that implies that BA belongs to R. So this relation is also symmetric. And finally, we have to figure out whether this is a transitive relation or not. Now consider AP belongs to R and PC also belongs to R. That is A minus B, that is divisible by n, and B minus C is also divisible by n. So then we can say that A minus B is actually equals to some n p, and B minus C is actually equal to some n k. So now we add them together. So that should give us A minus C is actually n is n times t plus k. So this implies that n divides A minus C. So this implies that AC also belongs to this relation R. So this implies that AC, so this implies that R is a transitive relation. So this relation that AB is related to R if and only if A minus B is divisible by R. So this is actually equivalent to A is related to B if and only if A is congruent to B mod A. That is, we are considering A and B to be related if after dividing A by n, we can get the residue as B. So this is nothing but the residue class. So we have seen Zn or Zp, those kind of classes. So those are basically same as this relation. So this relation basically implies that. Okay. Let's go to problem 10. Then problem 10, we are given a partial order set. So a partially ordered set is basically has to be three relation. One is reflexive, transitive, and antisymmetric. So symmetric relation was that if AB belongs to this set A, sorry, AB belongs to this relation R, then BA should also belong to the relation R. What antisymmetric says is that if AB and BA both belongs to a relation R, then we must have A is equal to B. So that's what antisymmetric relation is. And for partial order set, we can call S to be a partial order set corresponding to this relation. So instead of this relation R, we just we uh, usually use this notation, that is this equal to sign. So this relation is called a partial order set if this relation is reflexive, transitive, and antisymmetric. So if these three conditions are, then we can call it a partial order set. Okay. So now any element x in this partial order set is called okay, for any subset P of S, an element x is called a minimum set of P. If x is in P and x is less than equals to y for all y in P. So that is called the minimum set. So this is the definition of minimum set in a partial order set. Anyway, uh, so now we have to prove that if every non-empty set S has a minimum element, then S is a totally ordered set. So we have to prove that if every non-empty set, that is for all P not equals to phi non-empty set and P subset of S, okay. So we have two statements over here, that if every non-empty set, a subset set, has a minimum element, then we have to prove that S is a totally ordered set. So this is what we are going to prove. So this is our statement P and this is our statement Q. So we have to imply, so we have to prove that P implies Q. So in order to prove this, what can we do is that we can just prove that P and not Q should give us a contradiction. So if we do that, then that should give us the, so that should prove that P implies Q. So what we are going to assume is that this first statement is true, that every non-empty set S has a minimum element, and we also assume that negation of this statement, that is S is totally ordered, this is also true. This we assume that S is not totally ordered. So what's the definition of totally ordered? So totally ordered says that there for every pair X and Y in S, X and Y should be comparable. That means that either one of these two is true. So either we have X is visible Okay, so the definition of totally ordered set was that any two element in the set S that should be comparable. So therefore, the negation of the statement should be that there exists an X and Y such in S such that X, Y are not comparable. So there exists some X and Y which are not equal such that this X and Y are not comparable. So this is what we have. Now, let's say that T is actually equals to this set X and Y. So T is a proper subset of X, is a proper subset of S. Then according to the statement P, it says that T is a non-empty subset and non-empty subset of S, so it must have a minimum element. So without loss of generality, assume X is the minimum element. So if X is the minimum element, then what can we say about X? So according to our definition, it says that X is actually in T, which is true, and X is less than equals to any T for all T in T. And since we know that this Y belongs to T, so then we must say that X is less than equals to Y. This is also true, but this cannot be true because according to our assumption, there exists this X and Y which are not comparable. So this X and Y, they are not comparable. So neither this is true. So this is not true. And also Y is equals to X. This is also not true. So none of them is true. But over here, uh, we have come to this conclusion that X is less equals to Y. And this is true. So this is a contradiction. Therefore, our assumption was wrong. That is, the assumption that S is not a totally ordered set. This is not true. So it must be a totally ordered set. So this is a proof that P implies Q. Okay. So now over here we have for any set A, and there is a surjective function from A to A. Then F must be a bijective function. So this is what we have to either prove or disprove. So till now we are only looking at finite sets only. So if we consider this set A to be a finite set, then the cardinality of set A, let's say it is n. So now we are given any surjective function f. So f is a surjective function. So what is the definition of surjective function? So surjective function, the definition of surjective function was that we consider any element in the codomain set. So this is called the domain set, and this is the codomain set. So if you consider any element in the codomain set, then corresponding to that element, you will always have an x in the domain set, so that f of x is actually equal to 1. That means any element in the codomain set must have a p-image. So that was the definition of surjective function. So in other words, the image of f. So image of f means that if we consider each of the element in A, and if we just map all those elements to the codomain set, then the elements of all those images, the set of all those images, so that is the image of it. So this should actually be is equals to the cardinality of it. This is since f is a surjective function, then we can say this. That is image of f which have the cardinality exactly n. So this comes from the surjection. Now it says that f also should be a bijective function. So it is surjective function already. If so now we have to prove that this is a one-to-one function in order to prove that this is a bijective function. So let us consider. So let's assume f is not one-to-one. So if we assume that it is not one-to-one, so what does that mean? So that means that there exists some AB in the set A such that f of A is equals to f of A. So it is not one-to-one means that there exists some AB such okay. So AB which are not equal. There exists AB such that AB is not equals to B and f of A is equals to f of A. So that means that there exists some two elements A and B which is mapping to same element in the codomain set. In one-to-one function that should not happen, but since we are assuming that it is not a one-to-one function, so this should happen. Okay, so now over here in the set of A, so apart from AB, this set, so there are total n minus too many elements. So these are the two elements of A of the set A, and there are total n minus too many elements in the rest of the set A. So these two elements is mapping to one single element. Okay, and the rest of the n minus too many elements, they can map to at most n minus too many elements in the set A. So then the image of F, the cardinality of image of F, that should be n minus too many elements. Okay, so that should be less than equals to n minus 2 plus 1, because these two elements is mapping to only one element, one single element, and the rest of the n minus 2 elements, they can map to at most this many elements. So therefore, we can say that the image of the cardinality of image of F, that should be less than equals to n minus 2 plus 1, which is nothing but n minus 1. So previously, since F was surjective, so therefore we had already assumed that image of we already had the result that image of the cardinality of image of F is actually equals to n. So this tells us that n is actually less than n minus 1, less than equal to n minus 1, which is absolutely not true. So therefore, this is a contradiction. So our assumption was wrong. So our assumption that F is not one-to-one, this is wrong. So F must be one-to-one, and F is also surjective. So definitely F is bijective. Now we have proven that F is bijective only with the assumption that A is finite. If the set A is finite, then definitely F should be F with this particular any surjective map from A to A, that should be bijective map also. But what happens if A is infinite? Can we say that the same result holds for that? That is, if we find a map A to A which is surjective, this should also be a bijective map. Can we say that? And the answer is so. In that case, also we can that is that should actually be so for infinite case this is actually not true. Basically, we can give an example. So the example can be for yeah, okay. So this can be treated as an example. Oh no, it is infinite map Uh, okay, so consider this one. So consider f of n is equals to n if n is even, and n minus 1 if n is odd. Okay, no, no, this is not a surjective map at all. Okay, yeah. So if can be considered as this. So f of n can be considered as n over 2 if n is even, and n minus 1 over 2 if n is odd. If we consider this one, then how? So is this map surjective? So if we consider any k in A, sorry, this map is defined from Q to Q. No, sorry, not Q, Z to Z, Z to Z. So from integer set to integer set. So if you consider any integer key like this, then 2k, so f of 2k should actually be equal to k as defined over here. So therefore, this is definitely a surjective map. So this is definitely a surjective map because for any k we have a image in the integer set such that f of 2k is equals to k. Now the question is whether this is a one-to-one map or not. Because if this is a one-to-one map, then you can say that this is a bijective map. But our target is not to prove that is to prove that this is not a bijective map. That is, we just have to show that this is not a one-to-one map. So as you can see, that if we consider 4 and 5, so what is f of 4 and f of 5? So f of 4, as you can see, that f of 4 should actually be, since 4 is even, so f of 4 should be 2, and if uh, if n is odd, that is over here n is odd, so 5 is odd, so in that case it should also be equal to 2. So if of 4, sorry, 4 and 5, they both map to the same value to in this mapping n. So this is surjective map, but this is not a one-to-one map. So this is definitely not a bijective map. Okay, so and this is possible when a is infinite. And therefore, if A is set, A is infinite set, then this is not actually true. Then we can give an example, and the example is this mapping F, for which we can say that this is not a bijective map. F is not a bijective map. But definitely, when A is a finite set, then this is true. Okay. So now we are given a R and equivalence relation on a set A, and the cardinality of A is 30. Now let R partition A into three equivalence classes. So there are three equivalence classes, A1 into A3. And if the cardinality of A1 into and A3 is equals to are same, then what is the value of the cardinality of R? So now, first of all, consider n many points. So there are this n many points. Now consider that all of these n many points are in the same equivalent classes. Then, and if they are related to each other, then we can consider a line among them. So since these are all in the same equivalence class, then we can consider all possible lines among them. And corresponding to each of these lines, okay, so these are not all possible lines. I'm just giving an example. So these should also be a line, this should also be a line, and this should also be a line. So among each of the pair of this points, there should be a line, and this line represent the relation, the pair A B in the relation R. Okay, so if there are n many points in a equivalence class, in a particular equivalence class, then corresponding to the equivalence class, how many pairs this AB pair should be in the relation R? So that should be n square many. Since there are n many points, so n square many pairs can be possible. So all these n square many pairs should be in the relation R. So now the question is that we are given a set A with 30 elements, and this is divided into 3 equivalent classes such that A1, A2, and A3, their cardinality are same, and that is only way possible with each of these A1, the cardinality of A1, A2, and A3 is nothing but 10. So that should be the cardinality of A1, A2, and A3. Okay, so this is one equivalence class, and it has 10 elements. This is one equivalence class with 10 elements, and this is also an equivalence class with 10 elements. So now, how many relations, how many pairs does this constitute, this equivalence class constitute? So that will be 10 square. For this also, this is 10 square, and for A3 also, this is 10 square. So the total number of pairs in the relation R, that should be 300. Okay. So now the question is a little different. So over here we have x and y sets such that the cardinality of x and y are given. So how many functions are possible from x and y? So if x have m many elements and y have n many elements, then there should be okay, so a1 into a3. Now this a1 into up to an, and over here we have b1 into up to bn. Now each of this a1, it can go to either of this n many elements. So a1 can map to any of these n many elements. So there are n possible values for a1. For a2 there is also n possible values, and similarly for am there are n possible values. So this is m times. So the total number of functions that are possible from x to y, this is actually n to the m. So this is the total number of possible functions. The second is the total number of injective functions. So injective means that no two elements should map to one same element. So there are a1 equal to an, sorry, am, and b1 equal to bn. Now a1 can map to any one of them, any one of the m elements. So the possible values for a1 is m. Now a2 can map to any one of those elements, but wherever a1 has already mapped, there it cannot map. So it can only map to m minus 1 many elements. Similarly, A3 can map to any of the elements, but wherever A1 and A2 has mapped already, there it cannot map. So therefore, m minus 2 many possible values for A3, and similarly, we would have m minus n many possible values for m. Sorry. Okay, this was m. So this is m n minus 1. So n minus 1, n minus 2, n minus m. So this is the total number of possible values. So, I mean, possible. This is the total number of functions from injective functions from x to y. You can simplify this and write it as n factorial over n minus 1 factorial n minus n minus 1. Okay, n factorial divided by n minus n minus 1. Yes. Okay. You can write it as this. So injective functions, and finally we have the number of bijective functions. So for bijective functions, x and y. Now, if we want to find the number of bijective functions, then one thing that we have to understand is that both of the sets must have same number of elements. So instead of in and m, we just considering there are total n many elements in both of the sets. Now, if we want to find a bijective mapping, so what we can do is that we1 to en and it is b1 to n. So we just give a permutation to this set, and let's say that, so this is one mapping. So a1 goes to b1, a2 goes to b2, and so on. So we give a random permutation to this particular set, and that will give us another mapping. So basically, the number of permutation on this set y will give us the number of bijective functions. So if there are n many elements, so what is the number of permutations on this set? So that should be n factorial. So one other way is to one other way we can compute this is just like the previous one. That is, a1 can go to n many of these points. A2 can go to n minus 1 many of these points, and so on. And finally, a1 would actually have only one possible point. So this will be like this. So n times n minus 1, n minus 2, up to n, up to 1. So that is something called n factor. So, okay. So now we are also given this SRS. So SRS basically is a denote the number of partitions on an R element set that is partitioned into S many disjoint subsets, non-empty disjoint subsets. And this is also denoted as a Stirling number of second kind. So there are also Stirling number of first kind and everything. So this is the Stirling number of second kind, which represents the number of partitions on an R element set into S disjoint non-empty subsets. So now what we have to do is that we have to derive a formula to find the number of surjective functions from x to y. So suppose that we have an x and we have a y. So x have m elements and y has n many elements. So what we have to do is that we have to find out the number of surjective maps. Surjective map. So yeah, surjective functions. So in order to find surjective map, so what we know about surjective map? So if we consider any y over here, then there should be a pre-image over here. There should be at least one pre-image over here. So what we do over here is that we, depending on the values in y, corresponding to y, we define this set C1. So Cy is basically the set of all x in the x such that f of x is equals to y. So corresponding to, for all y in y, we define this set C of y. Now, claim is that C of this C of y, the collection of all this C of y's. So this actually creates a partition. Why? Because if we consider that, so first we have to consider prove that this is actually equals to x. So in order to do that, first we have to prove that x is a subset of this union of all this y, and union of all this is actually a subset of x. Now this is true because each of the C of y, this is basically nothing but a subset of x. Now, if each of the C of y is subset of x, then union of all this C of y, and this is finite union because there are only finitely many set in y. So therefore, finitely many C of y's that we are doing this union. So therefore, that should be a subset of X. So that is true. But now we have to prove this. So we consider any arbitrary X into X. Then f of X. Let us consider y is equals to f of X. Then what we can say is that X belongs to C of y for that particular y, and therefore we can say that X belongs to union of the C of y. So this is also true. So since both of them are true, then we can say that X is actually union of this. So first part is done. The second part is that if we consider any y1, y2 which are not equal, then C of y intersection C of y2, they should be equal to 5. If possible, let us consider that X belongs to this cy1 intersection cy2. So that means that f of X is equals to y1, since X belongs to cy1, and since also X belongs to cy2, so that should also imply that f of X is equals to y2. But since y1 is not equals to y2, this is not possible because it is a mapping, and this violates the condition for mapping. That means that one element should not map to two different elements in the coordinates. This is not true. So therefore, this is true. That is C of y1 intersection C of y2, that should actually be equal to empty. Okay. Okay. So now we have proved that if we have a surjective mapping F, then corresponding to that, we will find this C of y, this collection of C of y, which actually creates the partition of X. And this is a partition, and each of these sets are non-empty, because since we are considering this map to be a surjective map, so then definitely corresponding to each y there must exist at least one X which is in C of X, C of y. So therefore this is non-empty, sorry, partition of X into m many non-empty disjoint sets. Right? So basically, if we want to find, so corresponding to one surjective map, we have actually found this number of classes, yes, this number of classes corresponding to one surjective map. Okay. So now what we are going to do is that we are going to find the number of such partitions on a set, and once we find the number of such partitions, then we will find the number of these surjective maps in terms of that. So what is the number of partitions from X? How many ways can we partition a set X of n elements into m many disjoint subsets? So that is X n m, that sorry, S n m. So that's what we have seen. That is what starting number represents. So this is our many. That is this many way we can partition this set X. Now set X is now partitions into this element, this many non-empty subsets. Now over here, so there are m many subsets, disjoint subsets, and over here we have m many elements, V1, V2, V3, and here. Now let's say that we are representing this sets as C1, C2, C3, up to C. So we are just enumerating them. So now how many ways that we can map this particular class or particular set to one of these elements? So this mapping should be done in an injective way. That is, C1 is mapped to, if C1 is mapped to V1, then we cannot C2 or C3 to again to V1. So we cannot do that. So this is basically the number of injective maps from set of m many elements to set of m many elements. So that is m factorial that we have already proved. So n factorial ways we can map each of these classes to each of the corresponding elements over here. And how in way we can do this partition? That is S n, right? Sorry, S n n. So with S in n ways we can partition this set of n many elements into n many disjoint subsets, and this n many disjoint subsets can be mapped to this m many elements in m factorial ways. So this is the total number of surjective maps. Okay, so so this is the end of today's session. So if you have any questions, you can ask me now. Otherwise, this is we will meet next week. Thank you.